Recording. Okay, great. Thanks for joining us again. This is our third session of going through the statistical mechanics of learning. And today I wanted to go through what's called the student-teacher model. So the student-teacher model is a classic setup from statistical mechanics where you can compute the generalization error of perceptron. This is a very old stuff from the 1990s. In the paper, we discussed this sort of in section 4.3 and 4 and the rest of section 4. We go through a very, very simple model, simple explanation of this, which you really don't need to know a lot of statistical mechanics to understand. And then in the appendix, we do all the, we do the statistical mechanics treatment. Mostly, it's still in the annealed approximation. If you go back to the original literature, it's even more complicated than what we're doing in this paper because you have to do replica calculations. And I'm happy to go through that with anyone who wants to do it at some point. But the point of this section of the paper is just to introduce the basic setup in a really straightforward way. And so, again, just please ask questions as we go. So the idea here is, in this subsection, we describe the basic setup of the student-teacher model for computing the average empirical perceptron generalization error. So I could denote that as this E empirical. And we'll do so for a simple linear perceptron when the students and teachers are modeled as vectors, as in the traditional statistical mechanics of learning, in the annealed approximation and at high temperature. So we're always going to be, from now on, we're going to be using linear perceptrons in the annealed approximation at high temperature, and everything simplifies tremendously. And you can do a lot of this just using some basic calculus. So for a simple perceptron, one can use the student-teacher model to derive an expression for, again, the student-teacher generalization, and one obtains different expression depending on the type of perceptron: linear, Boolean, the type of ensemble, the conditions of learning, the type of approximation, etc. So there are all these, in the original literature, there are all these different things you can do. Here we review the basic setup in order to give the reader a sense of the general approach and to give a background for how we can use these results to formulate our SETOL. So we're not going to look at all the different examples. That's stuff you can go to the original literature for. So we start with just the test error of the teacher. We start by describing how to obtain a simple formal expression for the empirical test error of the teacher perceptron. So again, imagine a perceptron, and again, this might be the model that you're trying to estimate something about. So maybe you're looking at DeepSeek or Llama or Quinn, and that's essentially the teacher in this model. And we want to understand the performance of this model, and in particular, the performance of the individual layers. So we have the teacher, we have a perceptron called the teacher that maps to some actual, i.e. correlated data, and we call it correlated data X mu in some domain D for some known binary labels Y mu of the teacher. So they say that T maps the data set, each individual instance, to some specific label, where the teacher perceptron is specified by some energy function. The energy function is essentially the output function of the neural network. So typically, what is the empirical error, right? So the empirical error for training would be I sum up over all the training examples, and I have the loss, and I take the label minus the output of the teacher. Notice the teacher is specified with this lowercase vector here. I mean, that's the teacher vector. So that's what we're doing. And again, this is just what you would do operationally, right? If operationally, you would just measure the loss, and this might, So we seek the true generalization error of the teacher, and we call the true generalization error gen. So it's not the training error, it's the generalization error. Of course, this is usually unknowable. We don't know the true error, right? There's no way to do this. And so in practice, we try to estimate it by measuring the error on some of the teacher predictions on some test or holdout set. So we call X sub superset sub superscript test. This is the test set, test label, and we call this the average generalization error. And so we say that the generalization error, the true generalization error of the teacher, is approximately the empirical generalization error, which we obtain by just measuring over the test set. This is all stuff you sort of know. And the goal here is just to sort of lay out the math and the formalism so you see what we're going to do later. So that's all we're doing here. So to measure the error, the loss function could be L1, L2, could be cross entropy. Whereas for training a model, it's usually, for training a model, it's usually my cross entropy loss. Here, we're only going to consider the L2 loss. And that makes things really simple. And by the way, it turns out there are some papers that show I have to dig it up. This paper shows it doesn't really matter what loss you use for sort of this theoretical analysis. They all sort of track the same way.
Wait, about that. So does that mean that you don't make use of the fact that L2 is convex and so on? Because like for instance, cross entropy is not, right?
No, no, we don't make use of the fact that L2 is convex. It's the loss is we the only thing we care about the loss. It's just going to integrate out. So the fact that we use an L2 loss allows us to integrate out the it allows us to integrate the data variables out. That's sort of the key idea here, and you'll see that um, you'll see that in a minute. So, but we don't use the fact that it's convex at all, actually. So, but it may be there implicitly, but it's not. Well, you'll see. So now we want to model the test predictions with student perceptrons. This is something actually I want some feedback on because in some sense in the literature they talk about modeling the generalization error using an empirical distribution of students. And there's a question of how you define the students. And so this is sort of the idea. So in most theoretical analysis, one employs random IID data. So not the actual training or test data. Certainly not real-world strongly correlated data to estimate the average error of, say, the trends in the generalization error of a model M. And sometimes I use this superscript to say E of M, but this is sort of I may stop doing this. We have too many of these. One of the problems with this paper is it's a little too many symbols. We will estimate the average or typical generalization error for a real system using real data, using techniques analogous to statistical mechanics. So we're going to estimate it, but in fact so here we're just trying to describe what you would do with real data. And in a theory you don't use real data, you use Gaussian data. And so there's going to be this connection, like how is the real data connected to the Gaussian data? And there actually is a duality between the real data, between the weight mate. Well, I'll talk about that in a little. It's not in the paper. We can talk about that afterwards. So to do so, imagine having another perceptron called a student with the same architecture acting on the same data set. The student tries to reproduce the teacher predictions. So this is sort of the trick here is how you define this. So the student could either reproduce the teacher predictions or the student could reproduce the true predictions. And this is sort of the catch here. Are you reproducing the teacher predictions or the true predictions? And the reason for this is, and this is something which I want you to think about. In one case, I think we're actually reproducing the generalization error, the accuracy, and in another case we're reproducing the precision. And I don't really talk about that yet in the paper, but this is kind of why I wanted to go over this, to think about this idea that we can reproduce the not so much the error of the model, but its precision. How different. In other words, if the students are trying to reproduce trying to reproduce the teacher, then what we're going to try to do is understand how much variation there is in the teacher's predictions. So in other words, you imagine you write down you have these labels for the teacher and the student in terms of perceptron energy output, and you write them down. So the teacher prediction is the output of the teacher vector times x of mu, and the student prediction is the output of the network times the student vector times mu. And we didn't really define yet the student teacher vectors, so that's sort of missing. I need to kind of put that at the beginning here. And then the perceptron output. So in other words, for a perceptron, it's just the vector dot product between the perceptron weight vector and the training set, the training or test data vector. So the output Tx is just H times T vector, teacher transpose X, and the student energy is just some activation function S transpose times X mu. So H is just some simple activation function like a Heaviside step function, or just the identity. Here, we're only going to be concerned about the identity. For a linear perceptron, we use the identity activation, which in the case we obtain the very simple expression. The label is just the teacher transpose times X, and the student is just the student vector times x. This is actually a classic model for, and of course, this is not, these are real variables, right? They're not binary. So you have this case where you're taking a binary problem and you're trying to treat it with basically like a linear regression where you get real variables. This is actually a really classic approach to how to model a perceptron, and it actually goes back to the original papers on double descent, and I have a blog post on this of why we do it this way. But this is, it's right now, it's just to make the math really simple. So the idea is so now the idea is that, again, this is just stuff we're imagine doing operationally. Like you could operationally do this. So to train the student perceptron that can learn how the teacher perceptron labels the training data, one could break the training set. You could break the training set into training and test, right? And you could then try to find, you train these models on the optimal model weights and then evaluate in the test data. So like if you were doing this, you would actually train a student, which, you know, to try to emulate the same predictions as the teacher. Here the thing is that, so you would end up with the student learning task can therefore be written as equation 2 as the following optimization problem. So you try to find the optimal S vectors over all the training data where you look at the loss between the student and the teacher. And again, it really depends on what the labels are. You know, the student can be trained on the true labels or it can be trained on the teacher labels. But the goal here is to learn the student weight vector given the teacher vector. So if you have the teacher, you try to learn the student. This is what people do. It's, you know, this is what today they call student-teacher learning, right? Or distillation, where you try to, you know, people are trying to distill DeepSeek onto Quinn. And they're essentially doing this, right? So this is something people do all the time in practice. Notice that at the step, the student and the teacher both depend explicitly on the choice of the training data. So we could write, you know, S depends on the train and T depends on the train. We just don't do it that way. Now, given such a student, we could compute the teacher generalization error by replacing the test predictions with the student predictions. So, in other words, we're going to equation 72. So we go here, we're going to replace these Y with the student predictions. And then average over the test data, right? So if we were to go back and just take this and put the student in there, we could obtain the actual, we could basically average, we could obtain an estimate of the test error, but that's not what we're going to do. Well, excuse me, that's what we're going to do here. So if we have a very large number of suitable students, say drawn from some random distribution, we can try to estimate the average generalization error of the teacher. The empirical generalization error is given by an average loss, the average over all possible students, and then over all test data points. So, you know, you have this function which depends on the training data and the test data. We've already trained the model, and now we're just looking at how the student predictions differ from the teacher predictions. So the idea is we've trained a whole bunch of students, you know, a massive number of students, and we're just asking, we tried to distill, we tried to distill the model over and over and over. So we did like 1,000 distillations, and, we have sort of, we're going to average over the test data. But at some point we also want to average over all the students, and we haven't described that yet. So here, this is for a single student. So we're over a very, very large data set. So, and again, the loss could be L1 or L2. At this point, it doesn't matter. But the idea is when you average over the students, you're saying, in other words, I'm taking the loss between the student and the teacher, and you see this bracket, I'm averaging over all the students. And the idea is that this bracket should be a thermal average. Like, you shouldn't just do a naive average over the students. What you should do is average over the students in such a way that you weight the average based on how close you think the student is to the teacher. So that's sort of the idea of statistical mechanics, is that instead of taking this average on the outside, this bracket S, it could be just a simple average in the high temperature, but technically you want to do a thermal average. And what happens in the high temperature limit is that that thermal average simplifies greatly. But this is sort of the idea of statistical mechanics, and this is not explained properly here in this section, but the idea is that why you take this thermal average, and we sort of described this last time, is that if you were to average over all possible students, you want to do it in a way where you weight the student. So in other words, you have some notion of how close the student is to the teacher, so that you're not just averaging over all. You may have trained them. Maybe when you train the student to try to reproduce the teacher, you didn't train it for long enough epochs, or something went wrong in the training data, and the student's very, very different from the teacher, and that shouldn't count as much when you do this average. And that's the idea of statistical mechanics, is that you're going to weight how much the student depends on the teacher. And so this is not particularly clear, but then the other thing is that, and it's not described well here in this section, so I'll try to explain. The other thing is that what you want to do is you then want to switch the order of these averages. So, you could average overall, you could train all the students and then try to take, so you have like 100, you have 100 distillations of DeepSeek, and then you evaluate those distillations one by one. Or you could try to, switch the average. And so the idea is when you switch these averages, you would first, so I'll kind of describe here the idea that in statistical mechanics, we're going to be able to switch the order of the averages so that we average over the data first. And that's what we're going to do in the theory. So technically what we're doing here is called quenching, because you average over the models first, and then you average over the data. I'm not going to go through this section because I think it's going to be somewhat confusing trying to read through it, but this is where sort of the idea of where we're starting. And the idea is we want to switch the order of these averages so that we can somehow average over all the data first and then average over the teacher. And that's what we're going to do in the next section. So I'll sort of skip down here and we'll sort of start here and see what happened. So we have this. The idea now, before we had trained the model on real world data, X. And what we want to do is we want to model this data as if it were Gaussian data. So there's this figure that got moved from way up here. So we have this real world data, and we sort of talked about this before. We're going to model the real world data. We're going to make a model of data. So this X and mu are the things we actually measure in doing an experiment. Like, this is the actual training data for DeepSeek, and this is its labels. And here we're going to replace X with a Gaussian model. So instead of being real world correlated data, we're going to have this Gaussian model of the data. And the Gaussian model will be such that each of these vectors is in Rm, where m is the number of features, and they're going to be normalized in such a way that their Frobenius norm is 1 over m. So we can go down here, and that's what we're going to do when we set this up. All right, so we have this data model. To develop a semi-empirical theory of the teacher generalization error, instead of training and evaluating a neural network model using real data, we seek a simple analytic expression with parameters that can be fit to empirical measurements. So in addition to using a model for a neural network, we must specify a model for the data. In a real-world neural network, the data is correlated, in fact, strongly correlated, and this is reflected in the weight matrices. However, to be tractable for our starting expressions, or use uncorrelated data. Formally, we must replace the correlated data with some uncorrelated random model of the data. X goes to psi, as described in this figure. Our data model is a standard Gaussian model for the input data. Psi, each example of the real-world data becomes a Gaussian vector, where n0 denotes a Gaussian distribution with 0 mean and u invariance. Psi mu is normalized such that the Frobenius norm is 1 over m for all data vectors. And I just make it clear that that is actually the Frobenius norm, since there might be some confusion over that. So we make this distinction between actual and model data to emphasize later that we'll use our so-called semi-empirical procedure to account for real correlations in the actual data. You know, I posted something on the general channel and on Twitter the other day where I described this idea of there's this duality. There is a duality between the weight matrices and the data. There's this sort of inverse duality. And probably, I don't know how much I should talk about that here in the paper, but it's this idea that, and we could talk about, I don't know if anyone saw that Twitter post, but it's this idea that when you train a model that you typically would choose the weight matrix as as basically the inverse covariance matrix of the data. So like when you train a Hopfield model and you ask, well, what is the weight matrix or for the perceptron of a model, it would actually be the inverse covariance matrix of the data. So there's this sort of duality between the real world data and the weight matrix. So, but here we go back. We say, here's the student-teacher model for the annealed potential. So the idea is that we model the student-teacher error with the teacher error with the average student-teacher generalization error, which is attained by first computing the student error over all possible input examples. So we define the data-dependent student-teacher error function, or the energy difference. So this is now over all all possible input examples. We have the difference between the student output and the teacher output. See, the idea is earlier I was trying to set this up. I don't know if I did a good job. I was trying to set up this equation 78 and then note, well, now we're going to kind of start again where we have this error, but notice that we don't have the average over the students yet, right? There's no average over the students. So this is just, again, L is just simply the L2 loss. This measures the error between the student and teacher. It is 0 when the predictions are identical, and is non-zero otherwise. I don't know why we need... Well, okay. We aim to develop a simple expression for the average student-teacher generalization error, and to do so, we define the annealed error potential for the data average student-teacher generalization error. And that thing is called, that epsilon should be here. But we talked about this a little bit in section 4 too. So this little epsilon is the data average, which is 1 over n, and I have to check the notation here to make sure where that, if that 802, it's this average. Typically we, when we average, we have a 1 over n times the measure over d mu of psi n times delta E. I just need to check this there. I need to check the definition here in 82 to make sure there's actually a 1 over n in that average. I think that's correct, but sometimes in reading the paper, I include the 1 over n when I define this object, and sometimes I don't. So I have to be a little careful in that. So I'm just making a comment to myself. But the idea is that you take an average, right? You're just taking an average. So the measure will end up being a Gaussian measure over n samples. And the intent is to evaluate this in the large n limit, thereby sampling all possible inputs in the space. Now, sorry, we're missing here. And by applying the annealed approximation, we can rewrite the average student-teacher generalization error first as a simple average over all possible inputs, and second as a thermal average over the students. So this object now becomes the thermal average of this. And this is what I was trying to describe before, where before we had the brackets inside the sum, and now we have the brackets outside the sum. So the idea is you average over the data first, and then you average over the students. And so this is what we call to be annealed. Whereas opposed before, and I'm sorry if this is a little confusing, if you average over the students first, and then you average over the data, this is called being quenched. So 78 is an example of being quenched, and I should make a comment there. This is an example of being annealed, where we take the average, the thermal average, we average over the data first, and then we average over the students. Okay, so what does it say here? In the classic StatMech approach, this is a thermal average in the canonical ensemble with beta fixed. That's explained in 4.2. Here, we'll do something similar, as the student average will be computed using association. Oh, here later. Here means in 580. It means later in section 5.5. You know, we're going to do this. So this is sort of a forward pointer, which we may not need. But the idea is later we're going to do something similar and take a student average where this S will be replaced with a matrix. And so we're going to compute it from the associated generating function, which we described earlier. Okay, so that's sort of just a pointer, which maybe you don't need to worry about right now. Recall that the empirical estimate dependent on specific instantiation of the model is quenched. That's what we're talking before, that things are quenched. For that reason, the final result, we need to take a second quenched average over all possible data sets. Here, we don't need to consider this and always work in the in-yield approximation. All right, so this part, I was just trying to explain in words the idea that we don't have to worry about quenching and doing these second averages and these sort of strange things they do in statistical mechanics. But all this is worked out in section A2. And again, this... All right. So now we're going to define this annealed potential. Now we're getting sort of the meat of things. So the annealed potential, and I'm sorry if things are a little confusing. This is sort of the first time I've read this in actually a couple of years. So just please ask questions as we go. So now here we're going to define the annealed potential as a function of the overlap. So we want an expression for the data average of the student-teacher error from equation 82, which is this average from the generalized from perceptrons to neural network layer weight matrices. We're gonna that we can generalize, not generalize, but that we can generalize. And so the idea can generalize. So for the perceptron, one obtains different expressions for the ST error depending on the type of activation function. The simplest are the linear and Boolean perceptrons, and for both L2 laws, epsilon is simply a function of the student overlap. This means we can write epsilon in terms of just a function of R, where R is the overlap, 1 over n times this overlap, which is 1 over n times the sum over m, SITI. So in other words, R is sort of an average overlap. It's normalized by 1 over n. So this is simply the dot product between the m-dimensional student S and T teacher weight vectors and normalized by the number of training instances. So for linear perceptron with activation function H, the error function is simply 1 minus R. And so here I have sort of this picture of the idea that in the simple perceptron model, the overlap is simply 1 over n times this sort of the overlap between these two vectors. And when we go to the matrix case, which is really what we're doing in the theory, this is going to be generalized to a matrix. And the matrix will be this trace between the layer weight matrix of the student and the layer weight matrix of the teacher, and R will then be 1 over n squared times trace ST. So the idea is we want to set up the student-teacher model sort of knowing that in the future we want to have some way of generalizing it to a matrix. And that's the idea of what we're doing here. Now we're just going to derive the student-teacher. And this is where the L2 loss stuff comes in. So you were asking about this. So the derivation. To derive equation 85, we define the data-dependent student error, or as this difference in terms of an L2 loss. So the error is simply 1/2. This is the L2 loss, student minus teacher transpose times student minus teacher. You can expand this out so we get, student transpose student minus 2 student transpose teacher plus YT transpose YT. This just becomes n minus y. So that now we just basically, we have this, this term that you have a 1/2, which cancels the 2. So we just pull this middle term out and we have this term called n, which is going to just be the overlap. N is just this ys transpose s plus yt transpose t 1/2. So that's just normalization of the vector. And so we get n 1 minus eta, where because they're in vectors. So in other words, this term plus this term is 1. This term is 1. We add them together, we get 2. Divide by 1/2, we get a 1. There's n components, so we get, they're n vectors because we're taking a sum, right? Because in this equation, in this equation, we're summing over n, so we get n of them, and we get n 1 minus eta, where eta is now just this term, which appears to self-overlap. So we call this the data-dependent self-overlap, and this was also defined a little earlier. So now we can define the error in terms of 1 minus its self-overlap. This expression is analogous to the student-teacher overlap R, but before the data has been integrated out. The self-overlap in ST psi will appear later in equation 5. I don't have I screwed up the reference there. When formulating the matrix generalized overlap operator. So the energy that this is like the standard trick. This is why we use the L2 loss. We use the L2 loss because we can do this trick and write down the error in terms of its overlap. That's why we do it. The fact that it's convex, maybe that's important. It doesn't come up explicitly. So now we have the error, the energy generating output function. We can replace the label the labels as simply these vectors. For each mu, for any mu, we can do this. And so we substitute them in. And so we write the student-teacher overlap as sort of 1 over n times the data vector times the student-teachers times the teacher vector times another arbitrary data vector. And in fact, this could be I don't have the subscript mu on here on 87. Maybe we need to have a mu here to make it clear. But this is actually like an entire matrix. Or really it's just a variable. It's not mu. It's just, psi here is just an arbitrary variable. So I don't have a subscript mu on here because it's just an arbitrary mu, but it's true for all mu. So it's just a variable. And so then when we average over the data, and there should be a superscript n on that, on 89 should have a superscript n on the average, because we average over all n, we just get 1 over n times the ST over. So we derive this expression for the self-overlap as 1 over n times the ST overlap. This is sort of the key idea. Now we want to evaluate epsilon of R, and to do that, we're just going to compute the average of the integral over all possible input data, which is an n-dimensional Gaussian vector. D mu is d psi of capital N P of n. So this d mu, the measure over the data, is just a multi-dimensional Gaussian measure with normalization in. And we're just going to put this in here, and we see that this object, then now you see I don't have the 1 over n, as I was talking about before, so I'm sorry about that. But this is 1 over the normalization times the measure, this measure of all possible data, times 1 minus eta. And if you go through, we substitute in 1 minus this overlap. This gives n over n minus that. You sort of go through. This becomes n times r, right? N r for the overlap. And this will then, because there are n of them, and then then we end up with this expression. And when you evaluate, and what happens is this is going, if we choose if we choose the normalization to be n, this goes to 1, and this object is just going to be normalized to 1 because we have the normalization. And because these are IID, so 1, 2. So I'm not explaining this well, but the idea is you can derive this expression epsilon of R for the self-overlap simply by assuming that you have an L2 loss and Gaussian data. And so if you evaluate this, you assume you have an L2 loss and Gaussian data, you end up with this expression 1 over R. That's what I'm trying to do here. I'm sorry, I went through all this and maybe I have a little trouble describing it, but that's the intent of this. And, maybe you try and go read it yourself and see if you can make sense of each of the terms. But that's the idea, is we have this epsilon, eta is defined as this overlap term, and you just integrate over the Gaussian measure. And when you do this and you set this normalization to n, you end up with this very simple expression for the error. So in statistical mechanics, the idea is one is interested in the total model generalization error, which depends on R. With these simple functions, this reduces to a function over R, and the SG generalization error is obtained by averaging over all the students. So you end up with this generalization. This is sort of the key result, is that the student-teacher generalization error is simply the thermal average over this annealed error, which is 1 minus this overlap, this average over the data, and then the thermal average, which is 1 minus eta, which is 1 minus 1 over n S transpose T, where again, this is in sample size, which then becomes just the thermal average of 1 minus R. And I'm sorry if I didn't explain it great. The point being, notice that the dimension m of the vector is irrelevant. So it actually factors out. So it doesn't matter how large your perceptron vector is, because in this simple model, it simply factors out because it's a Gaussian function. And so in the end, and then we're going to end up writing this thing called the quality. The quality is simply the accuracy, which is 1 minus the error. So the quality becomes 1 minus the error, the average thermal average of 1 minus the error, which is now the thermal average of the data average over eta. And again, this subscript here should have an n on it, because it's an average over all in data points. This is just the thermal average over the overlap once it's been integrated out over the data, which is just the thermal average of 1 over n S transpose T, which is just thermal average of R. And this is the key result. That so this is sort of really the key result of this whole thing, is that I can estimate the quality or the accuracy of a layer of a perceptron simply by looking at how many of the average of how the model overlaps with all possible students which try to mimic it. And this idea is what is used to define, this is the core idea which is generalized in Weight Watcher, to say if I can write a student perceptron and the quality of a student teacher model perceptron is just the average over R, then I can write the quality of a layer in a neural network can be described in terms of the matrix S transpose T. So instead of looking at S transpose, so here we have this sort of idea that it's very easy to generalize the linear perceptron in traditional system mechanics to a matrix. You have a total data error. So you have an error. In a linear perceptron, it's an error between the student and teacher vectors. In a matrix, it would be the error for each layer between a student matrix and a teacher, the weight matrix. You have a Hamiltonian, which we described it earlier in section 4.2. The Hamiltonian for the problem, somebody was asking about Lagrangians and manifolds. For the student teacher, the Hamiltonian is just 1 minus R. So in the linear perceptron, we derived this last week, that the annealed Hamiltonian is simply this potential, which is 1 minus R at large N. For a layer, we can define a layer Hamiltonian, which depends on this overlap matrix, which is the identity matrix over M, which M is, if the matrix is N by M, then we can define the Hamiltonian for a layer. If you want to define a Lagrangian, that would be the Lagrangian would be the Legendre transform of that. The overlap is simply 1 over n times the weight matrices between the student and the teacher. And the quality of that layer is, we have sort of this idea that the quality of the total model is the product of the quality of the individual layers, and the quality of the individual layer is given as 1 minus the generalization accuracy for the total generalization accuracy for the model, is the total accuracy of the model is 1 minus the generalization error of the model, which is then written as, in the high temperature limit and in high temperature yield approximation large N, this quality of the model, or basically the accuracy of the model, is given as a product over the accuracy or qualities of the individual layers, which can be written in terms of the Hamiltonian. So that's the idea of SETOL, and that's about, that's probably not a full hour, but this section's not as well flushed out as you can see, but this is the basic idea, that if I have a perceptron, and this is what I want you to take away from this. In the very simple model, if I have a linear perceptron, I can write down its Hamiltonian as 1 minus R, and I can write down the accuracy of the model, the generalization accuracy, as simply The generalization actually is simply the average over the overlap between all possible students and the teacher. So if I have, so theoretically, if I have some model, like it's like, DeepSeek, Llama, Quinn, I want to estimate the error. I want to estimate the error for that model, or I want to estimate the quality, which is 1 minus the error. I can do it for each layer simply by pretending that I have another model which mimics the outputs of that layer, and I just take a thermal average over all possible. I take a thermal average over all possible students of the overlap between the student and teacher. This is the idea, and this is the thing that we generalize later in the paper. So this old idea from statistical mechanics can be reinterpreted as in a matrix generalization for a more modern neural network. So this is the idea of this section. If you want to see more details, we can go to the end. Excuse me. 4. And in the end, in the appendix, we go through and actually derive the student-teacher model exactly using the full machinery statistical mechanics. And in the end, you end up with the same result. So what I tried to do in this section 4.2, in the end of section 4, sort of show that you can get this full result without using all the machinery statistical mechanics. If you assume I have a linear perceptron, an L2 loss, I'm at high temperature, you can just sort of do things naively, and you get a very nice result. And if you want to go through all the statistical mechanics, you can go through section 8, appendix A2, and we derive the entire result using all the formalism of section 4.2. And you still get this nice result where the error of the perceptron, or the Hamiltonian, is just given times beta 1 minus r, where the error, or this effective potential, this annealed potential, is just 1 minus the overlap. This is the core idea. So it's a very, very old idea that was developed in the early 90s. First, and there are many, many studies of trying to understand this particular model. For example, one of the things that came up, you can show, for example, that you can study the model with errors, without errors, with a linear perceptron, with a Boolean perceptron. There are lots and lots of papers which go through this simple model of the perceptron with different variations. And Mike and I have an earlier paper from 2015 where we sort of summarize all those results. But this is the basic idea. And I'm going to, I'll stop here. Where were we? We sort of stop at this big table, which is the end of this, the core result we have. And I'll just stop and let people ask questions. This is a pretty rough talk. I appreciate everyone sitting it through, and I'm just going to see if anyone has any questions. Okay, I have one mention in the general channel. Oh, well, no, it's something else. Okay. Okay, well, if anyone doesn't have any questions, I'm looking in the, I hope everyone can still hear me. I can't, I'm going to look in the, I don't see anything in the chat, so I'll stop there. I hope this wasn't too confusing. I'm happy to go through it again, or to sit down with you and just sort of go through and ask whatever question you have, or we can go through the appendix. It might be a little clearer to go through the appendix and sort of derive everything step by step, again, using statistical mechanics and all the formalism. And in fact, I was going to do that next time, so you can really see step by step how the formalism leads to these simple results, and how you can get more complex results. If you don't want to be in the linear perceptron, or you don't want to be at high temperature, you can do more sophisticated things. And if nobody has any questions, I'll call it a day.
Hey, Charles?
Yes, go ahead.
Yeah, were you going to further down the road maybe do kind of Weight Watcher examples?
We can do that next time if you want.
Yeah, I would love to, see it with examples. Yeah, it would be.
Sure. I'm happy to. Yeah, that's a good point. I'm happy to do that. In fact, we can even see, and I'll even show you sort of a. So I get to page 70. Yeah, Here's an example. I'll give you a quick one right now, just the preview. Here's an example where we train in section 6 of the paper. We train a multi-layer perceptron on a three-layer multi-layer perceptron on minced, right? So simple model, minced, right? Simplest thing you could do. And then we vary the learning rate. Okay, so we make the learning rate. So the learning rate is 1, 2, 4, 8. So we turn up the learning rate, right? And of course, as you turn up the learning rate, you expect the error to get smaller, right? Because it's learning faster. So you see, if I'm at like learning rate 1, I get an error of 20%. And as you turn the learning rate up, the error goes down. Now, what's interesting is as you can measure alpha, the Weight Watcher alpha, as you do this. So as you train this model, so we can measure it for layer 1, and we can measure it for layer 2. And you can see that as you turn the learning rate up, we double it each time. Alpha decreases until you get close to 2. When you get to the learning rates too large, test error goes up. All right? You've overfit the data because you made the learning rate too large. So you overfit the data. Alpha drops below 2. It goes like right below 2 for this layer. And for FC2, it again we do this like 10 times and we have these nice error bars. Likewise, for FC2 you increase the learning rate, alpha goes down. When you get to the test error, alpha drops. It's 2.1. It's very close to ideal. And so what we argue is happening here is that in layer 1, as you jump the learning rate up, you overfit the data, alpha drops below 2. So that's another thing that happens as that happens. Here's another example. When you do the batch size, you can decrease the batch size and you get the exact same effect. And what's happening is that, I can find it. If you make the Weight Watcher plot, you can see as you plot the spectral density, as you increase the layer learning rates, you can sort of see this plots. No, not this one. Let me try to find it. It's up a little higher. Yeah. Here it is. So as you increase the learning rate, the Weight Watcher will produce this plot for you. And it compares the weight matrix to its randomized form. So the red is the prediction from random matrix theory if the layer were random, and green is what you get in reality. And what happens is as you jump from 16 to 32, you overfit the data. And so if you randomize the weight matrix and then you plot its spectral density, you get this weird outlier here. This is the largest I've taken the weight matrix, forget FC1 and layer perceptron. I randomized the weight matrix and I plotted spectral density, and you get this weird outlier, which shouldn't be there, right? What is that? This is a random matrix. If I have a random matrix, why do I get it? And I plot it should follow the prediction of random matrix theory. What's this weird outlier? This outlier is a rank 1 perturbation in the weight matrix, which appears to be associated with the overfitting. So you can use Weight Watcher so what we're showing here is that as you use Weight Watcher, you train your models. You can track the individual layers to see how well they're doing. And as alpha goes down, you see the error goes down. And what we argue is that there's some sweet spot here where the error is minimized and alpha reaches 2. And if the error jumps back up and you overfit, if the layer overfits, you see this, you can detect the overfitting by this weird correlation trap, this weird rank 1 perturbation, which appears in this plot. And that, and we're not entirely sure what these rank 1 perturbations are, but you can see them. We're not entirely sure, and they're not necessarily bad, right? Maybe overfitting the data isn't a bad thing. Maybe it's something you want to do in some cases. But in certainly simple models, you can see that this rank 1 perturbation appears to be associated with a decrease in test accuracy. So this is what the theory is showing you. And there's some other things you can do as well. There's another metric called DEDX, and DEDX is this, and we have another plot where DEDX is another part of the theory. and there's this purple and red line. And so when you run Weight Watcher and you say dead x equals true, you'll get this. This again, the same idea. I increase the learning rate, and the accuracy is getting better, and these two lines get closer. So the purple and the red lines get closer. And this is a core prediction of the theory. Like this 120-page paper, all it's doing is trying to predict that this purple line should approach the red line. This is literally what the paper's doing. And you see it, and this is a condition of ideality. So when the red line and the purple lines line up, theory predicts that the layer is ideally trained. And this is actually a prediction of the theory. And you can plot, if we make this a delta, and we just plot this, we call this difference between the purple and the red line delta. And we put that delta on the y-axis and alpha on the x-axis. You can see that as alpha approaches 2 for a layer, again, this idea, we change the learning rate. As alpha approaches 2, that difference between the purple and the red line goes to 0. And if alpha drops below 2, that difference drops below 0. And depending on the quality of the model, you sort of get these plots that look like this, where we think that, at least for layer 1, things are behaving really well. So the idea being that there are certain layers that are trained really, really well in your model, and you see really clean, perfect predictions with theory. There are other layers which maybe aren't quite so good, and the connection and the layer is not so, the theory is not so perfect. And we can actually see this behavior in actual other models. So you can take this same plot. You can do VGG, you can do ResNet, you can do Visual Transformer, you can do DenseNet. You'll see the same behavior. So the same predictions of the theory, that as the alpha approaches 2, these conditions for ideality hold. And you can also see it in Falcon, in Llama. You see these same kind of plots that as your layers get better and better, these two conditions tend to approach each other. And sometimes they're almost exact. As the models get bigger, these things get better. This is what Weight Watcher is doing. It's letting you measure the quality of your individual layers, and it's giving you a prediction saying, there are these different quality metrics, and as these quality metrics start to align, theory argues that the layers are getting better and better. That's the TDLR of what's going on in this paper. It just it takes a lot of. Was that helpful? Did I lose you?
It's great. Yeah, no. It's good to see. Yeah.
Yeah, no, and it's it's. I tried to do all this in the blog post, but it's taken me, like 100 pages of mathematics to derive, and it's still typos, just to derive, this simple result, which is that, this simple result that these two lines should approach each other, and that these two lines, there are two independent quality metrics. This is HCSR theory. The x-axis is HCSR theory. That's the old paper. The y-axis is the new paper. And so it's taken me all this math just to prove that this happens. And so the proposal is that if you're training your own models, you can measure these metrics, and the theory says that these metrics should get closer and closer to ideality. Your model should perform better. Assuming that the data is not completely bananas, right? I mean, if you train a model on some crazy data, I don't know what it's going to do, right? But given that you've picked a good data set, that you have a data set that's reasonable, that the theory says you should get, this is what the theory's saying. And you can use the tool to monitor your layers and maybe even do things like adjust the learning rates on the individual layers to try to get them to converge better. That's what we're trying to do with the theory. And I'll comment that this result, this came pure out. This alpha was something we measured empirically, and we sort of understood it sort of through random matrix theory. This result on the y-axis, this is pure theoretical physics. Like that result came out of trying to derive an expression for alpha. And so this thing is what's called Wilson exact renormalization group. The fact that these layers exhibit the scale invariance from Wilson renormalization group, and you can measure it. That's sort of the key result of this paper. And and the goal is to have, eventually I'll write like a 1-page PRL or something, but the goal is to have some paper we can put on the archive that describes all of this pedagogically, so you can understand every derivation from first principles. And I appreciate you guys sitting through with me as I try to go through these derivations, which have been, they're very, very hard to make pedagogic. So there you go. There's your going. I encourage you to try using the tool, measure these things, come back to me, tell me what you find. Cool. Any other questions?
Thank you.
No, it's my pleasure.
Yeah, no. Thank you, Charles.
No, thank you guys. I really appreciate you humoring me as we sit through all this.
Yeah, thank you.
Great. And if anybody else wants to do a presentation, I'm happy. Like if you want to do next week, you guys want to talk about a paper or do something, happy to do that too. I'm sort of trying to just get a little group going where we can talk about this stuff.
Yeah, personally, I don't think that I have the expertise, but I would be happy.
That's how you get it. When you read a paper out loud to someone, it's when you read it by yourself, it seems correct. When you read it out loud like this, you really notice like, oh man, this is not so correct. And it really helps to read things out loud. I really encourage you when you're reading things to sit down and try to read them out loud and explain them to someone, because it really forces you to understand. You can fool yourself if you read your own words. But when you have to explain it to somebody else, it makes a big difference. Hey, Morgan, thanks for coming. All right, guys, we'll try to do this next week. I really appreciate it.
Thank you.
Okay.
My pleasure.